Hello and welcome to this session in which we are going to analyze a diesel engine. So we have been given that we have a diesel engine with a compression ratio of 20:1 ratio. So let me first draw the PV diagram. So we have a compression like this, and then a heat addition at constant pressure, and then an isentropic heat rejection, an isentropic expansion and followed by heat rejection. So 1 to 2 is the isentropic compression, 2 to 3 is the constant pressure heat addition, 3 to 4 is the isentropic expansion, and 4 to 1 is the heat rejection. So state 1 is given as 95 kilopascal, 290 Kelvin, slightly below the atmosphere because it's a suction process. State 2, so because the compression ratio is given as 20:1, the specific volume at state 2 will be 1/20th the specific volume at state 1. Okay. Moreover, the entropy at state 2 will be the same as the entropy at state 1 because it's an isentropic process. It's an isentropic compression process. Now state 3, because we are adding heat, so state 3 will be at a temperature of 1800 Kelvin, which is the maximum temperature given, and the pressure at point 3 will be the same as pressure at point 2. Coming to state point 4, the entropy at state point 4 will be equal to the entropy at state point 3, and the specific volume at state point 4 will be equal to specific volume at state point 1. So the first point is quantified in terms of the pressure and temperature, the second in terms of specific volume and entropy, third in terms of temperature and pressure, and the fourth in terms of entropy and specific volume. Let us proceed to the computer and see what we can get out of this. So P1 is 95, T1 is 290. So I've set the units in ES to be in Kelvin. V1 will be the volume of air at T equal to T1 and P equal to P1. As per the information about the compression ratio, V2 will be V1 by 20, and S2 will be equal to S1, where S1 equal to entropy of air T equal to T1 and P equal to P1. So far so good. So now with the help of S2 and V2 we can find out P2. P2 is pressure of air at V equal to V2 and S equal to S2. So let's see what the pressure is. So the pressure comes out to be approximately 5.9 megapascal. That's a lot of pressure. So P3 will also be correspondingly equal to P2, and T3 will be also equal to 1800 Kelvin. So then S3 will be entropy of air at P equal to P3 and T equal to T3, and S4 will be equal to S1, V4 will be equal to V1. So now that we have all the points, let us find out the net work. So if you recall the first law for a cycle, closed integral of the total heat added will be equal to the closed integral of the total work done. So because of this, we can write QH plus QL will be equal to the net work, where we will account for the sign of Q appropriately. So the heat added is during the process 2 to 3. So QH will be equal to H3 minus H2 because it's a constant pressure process. The heat addition will not be simply the difference in the internal energies. So this should have been covered in theory class. In case of a constant pressure process, the heat added will be equal to the difference in enthalpies and not the internal energies, because you are already accounting for the constant pressure work as PV. So U plus PV will become H. This should be clear by now. But the QL will be equal to U1 minus U4 because the heat rejection is going on during process 1 to 4. So during 1 to 4 the process is constant volume, and as a result it will be simply u1 minus u4. So the task now remains is to find the internal energies and the enthalpies. So u1 will be int energy air T equal to T1. So let us write down the expression for T2, because we will need the temperature to find out the internal energy at point 2, or rather the enthalpy at point 2. So H3 is simply known because the temperature at point 3 is given as the highest temperature achievable in the cycle, which is T3, which is 1800 Kelvin, and U4 is the, so T4 we can find out using S4 and V4. So with the help of this and the heat, we have eta is equal to W by QH. This defines the thermal efficiency. So the net specific work of the engine is 1065. There seems to be a small mistake. Because QL appears to be 0. But let's have a look what is wrong. So T4 has come out surprisingly to be 290. So let us see what is wrong. So this is the mistake. S4 is not equal to S1, rather it is equal to S3. So because of this small mistake, we were able to get points 4 and 1 identical. Okay, so the QL is equal to minus 430. So we already seen that we did not account for the sign and wrote it simply as QH plus QL. But because QL is negative, we understand that the process from 4 to 1 is losing heat instead of gaining heat. The heat gained is 1065 kilojoule during process 2 to 3. As a result, the work is 634.1 kilojoule per kg, and the thermal efficiency of the cycle is 59.56%. So with this we conclude this session on diesel engine, and I hope it will be clear on how to solve such kinds of questions as and when you encounter them. So with this we close this session. I'll see you next time. Bye.